Draw the Lewis structures for the following atoms. You've got GE, TE, and BA. First of all, let's find each of these on the periodic table. We've got GE. I don't remember what that one is off the top of my head. TE, germanium, and then not geranium. I'm sure TE and BA. BA.
It's down on the second row.
Get to back. GE, TE, and BA. So we're going to do the Lewis dot structure, electron configuration. So the electron dot or the Lewis structure for all three of these, GE, TE, and BA. Let's just do them in order then. GE, how many valence electrons am I going to depict on my structure? 4. Okay, so it's column 1A, 2A, 3A, 4A. 4A is going to have the same valence and the same Lewis dot structure as every other element in that column. And we've been dealing with carbon and silicon quite a bit. So it looks exactly like them, except for the symbol in the middle is for that unique element with 4 valence, and they are set on all of the cardinal locations. Okay. TE, it has 2 more. See, from going from 4 to 6, it has 2 more valence electrons. Column 1, 2, 3, 4, 5, 6A. So it matches we're going to place 6. And remember, we're going to start at the 3 o'clock and just go around 1, 2, 3, 4, 5, 6. In barium, BA, column 2A, so it has 2 valence electrons. 1, 2. This first one, the second one, and the third one. Any questions on those structures? Make sense? Okay. Number 2, right into the overwhelming request for number 2. It says, give the chemical formula for the following molecules. We've got aluminum sulfide. I'm just going to write it out here. Aluminum sulfide. We know that aluminum sulfide is made of 2 elements, right? Aluminum and sulfur. Let's locate those on the periodic table then. Sulfur's over here. It's a column 6A element. And aluminum is a 3A element. Is aluminum a metal or a non-metal? It's a metal. So it wants to gain or lose electrons. Which one? It wants to lose, not leave. Lose electrons. Don't take it so personal. I'm sorry. I'm trying to have fun. I know it's not coming across that way. I apologize. I'll try to remember it. Aluminum sulfide. Aluminum is a column 3A metal. Because it's a metal, it wants to lose, and it has how many valence electrons? 3. So if it loses its valence, what charge is it going to have? 3 positive. Right, 3 positive. I should have one more thing backed up. As we put these down, we recognize this is a metal and a non-metal, so we know what kind of a molecule are we forming. It's ionic. Okay, good. So it's ionic. Aluminum is a 3+. Sulfur wants to take on 2 additional electrons because it's a column 6A. It wants to become 8, so it wants to take on 2 more. It's a non-metal that wants to receive electrons. and so it wants to become a 2 negative. Using the shortcut then, we can eliminate the signs, transpose the numbers, and the formula comes out to be aluminum 2s3. Al2s3 is aluminum sulfide. Now, if you did that with Lewis structures, it would take you a lot more figuring, but you could do it. Yes, sir?
How do you get the 2?
Because sulfur over here is in a 6A. It's a 6A element. It has 6 valence electrons. So does sulfur want to gain 2 in order to have 8, or does it want to lose 6? Well, it's a nonmetal. It wants to receive. And so it needs to receive 2. When it receives the 2 additional electrons, each one is going to have a negative 2 charge. So what we do on this technique is to write the charge that it would like to take on. The aluminum wants to become a 3 plus. The sulfur wants to become a 2 negative. So we just eliminate the signs, cross them, and write them as subscripts. So the 2 is aluminum 2, the 3 becomes S3. If we did that using Lewis dots, we could logic this thing out. We'll just do this first one using Lewis dots. Al2S3. If we have aluminum and sulfur, we said aluminum has, I'm going to use X's this time so I can differentiate the 2. 3 electrons around aluminum and 6 around sulfur. 1, 2, 3, 4, 5. There's my 6. Okay, it's ionic, so there's going to be exchange. How many open slots do I have here? 2. I'm going to fill 2 of those slots from this first aluminum, but I still have 1 more to give away. So if I drew another sulfur, I could get rid of 1 of them and put it over here, but now I have an extra slot on this side. So let me put another aluminum down. I can transfer 1 of those to this sulfur. Now this is satisfied, but I got more electrons to give away. So I'll just repeat the process again. Sulfur, 1, 2, 3, 4, 5, 6. Okay, but I've got 2 to give away. I've got 2 addresses here. Transfer those 2, so they're no longer here. And see, now I have 2 aluminums that have given away their full valence, and 3 sulfurs that are completely satisfied their valence. So Al2S3. This is a longer way to do it, but you can reason it out. If you forget the technique, you can reason it out. If you use the technique and you have time to go back and check it, you can check your work by doing this. And all you're going to be using are aluminums and sulfurs. You're going to make sure that your metal gets rid of all of its electrons, and your sulfurs get completely satisfied with 8 electrons. And just keep doing it until you've got none and all. Any questions on that? Either this first technique, the shortcut, or the longer technique of using the Lewis dots. The second is iron 1 nitride. Iron 1 nitride. So I have 2 elements in play. Iron, atomic abbreviation or atomic symbol is Fe. Ferrous is the Latin word from which we get iron, ferrous. You might have heard of ferrous oxide, rust. So that's where it comes from. That's why you have ferrous and ferrous oxide. It's iron, rust. So ferrous, Fe, is iron. And nitride is the ide name for nitrogen. Iron is located here. It's in our D cell block for the prisoners of our periodic table. It's in the D cell block, and nitrogen over here is a column 5A element. Iron's a metal, nitrogen's a nonmetal. We've got another ionic bond that we're forming. Okay. looking at iron, what charge does this iron atom want to become when it becomes an ion? What is the charge of the iron ion that it wants to form? And how do we know? Right there. 1 positive, and how do you know that? The Roman numeral 1. The Roman numeral 1 tells you the charge that it wants to take on. It's a metal, it's going to be losing, so it's going to become a positive. It wants to become a 1 positive. Remember, these are the transition metals in the middle. So you're going to receive an indication by Roman numeral of how that particular set of atoms you're looking at want to react, how they want to act. In this case, the Roman numeral 1 indicates they want to have an ionic charge of 1. It's a metal giving up. It's a +1. Nitrogen over there is a 5A nonmetal. So what does nitrogen want to do in order to satisfy its valence? It has 5, and so it wants to take on an additional 3 and become a 3 negative ion. Okay. Wants to take on 3, become 3 negative. Wants to lose 1. So what are the proportions? Yes?
Finding those confuses me.
Say that again?
Finding the 1 positive and 3 negative confuses me.
Okay. One more time. Nitrogen is a 5A. Do you see that? It's a 5A. So nitrogen, when we write its structure, has 5 electrons in its valence shell. How many does it want to have all those addresses filled?
8.
8. It has 5. It wants 8, so it needs 3 more. And since it's 3 electrons, that's 3 negative particles. It's going to have a -3 charge when it's full. When the octet is full, it's going to have a -3 charge. That's why here it wants to become a 3 negative nitride anion. And here it's a +1 ferrous ion, or iron ion. Then having that, we can just, again, ignore the signs, but transpose the superscripts as subscripts, and it becomes iron 3 nitride. It takes 3 irons, each donating 1 electron, to give the 3 electrons that every one of those nitrogen atoms wants in order to become a nitride ion. So Fe3N. Any questions on that one? Since there was so much request for number 2, we'll ask everyone. Is there any questions on that one? Okay. 2C is magnesium oxide. Magnesium is a 2A metal. Oxygen is a 6A nonmetal. Metal, nonmetal, it's going to be ionic. Magnesium, the charge that magnesium wants to become, it has 2 valence electrons in the 3s2 orbital. It wants to lose both of those and become a 2 positive. Oxygen, this should look familiar. Oxygen is a 6A. It has 6, it's a nonmetal. It wants to receive. It wants to go from 6 to 8. So it needs to receive 2. Receiving 2 electrons makes it a 2 negative. If we follow the shortcut, it would be Mg2O2. However, remember, once we get to this point, that doesn't give us our final answer. Using the shortcut method, we then would look at it and say, okay, can I reduce this to common factor? Right? As I look at that, a 2 and a 2 are both divisible by 2, and so my final formula becomes MgO. MgO, the 2 and the 2. And if we did it with Lewis dot structures, it should be clear. If we have Mg, and it has 2 valence, 1, 2, an oxygen with 6 valence. 1, 2, 3, 4, 5, 6. We have 2 addresses, one here and one here, that need to be filled. Let's depict these as X's. One X is going to take up residence here. One X is going to take up residence here. And that gives me my completed structure. Now magnesium, because it has lost 2 electrons, has a +2 charge. Oxygen, because it has gained those 2 electrons, has a 2 negative charge. And because of the differences in the charges, those 2 ions are electromagnetically attracted to one another and stick together and form the molecule. Magnesium oxide, MgO. Questions? Did you remember on the shortcut to reduce it from 2s to 1s? Okay. And if you did the Lewis, it would hopefully just jump right out at you. Hey, I've got 2 empties, 2 availables, boom, there we go. Even trade, 1 to 1. And 2D, Chromium III oxide. We're going to have chromium. Where's Cr at? Chromium, oxygen, again, it's already circled over there. You're going to have a lot of oxides. An oxide is a rust, okay? Magnesium oxide, ferrous oxide, or iron oxide, chromium oxide. What that means is you've got a metal that's rusting. And when you have a piece of metal and you see rust on it, the rust is actually a molecule made up of the iron. Let's say in case of iron, you've got a block. Let's pretend this eraser is a block of iron. And on top of that iron you see rust. That rust is a molecule of iron oxide, or a collection of molecules of iron oxide. So when you see rust, it's called oxidation. When a metal reacts with the oxygen in the air and forms a new molecule, it oxidizes. So you'll see combinations of O's a lot because things rust. It's entropy, it's sin, okay? Works back into the chemistry. Things oxidize and fall apart. Well, it's part of this process. Chromium III oxide. We look at the oxygen first of all. It's a 6A non-metal. It wants to have 8, it has 6, so it has to take on 2. And when it receives the 2, it becomes a 2 negative. Chromium. Might be confusing.
Mr. Baker.
Yes, ma'am?
Could you send Lexi here to the office to go home, please?
On our way. All right, so oxygen takes on a 2 negative. I'll get this online as soon as I can. So oxygen has a 2 negative, and then the chromium, it's a transition metal. Because it's a metal, it wants to give up and not receive. Okay? So it's going to be giving up the electrons, and how many is going to give up? It's confusing because it's in a B column, but they've given us the Roman numeral 3. So we know that the charge, the ionic charge of this chromium is going to become a 3, and just remember, because it's a metal, it's giving up, so it's a 3 positive. So using the shortcut method, it becomes a chromium 2O3. That pretty much covers the review on 2. Any other questions on 2, since it was a popular request? Any more questions on how to solve the number 2 questions? Those of you that came in confused, you understand it now. Okay, good. Good. Number 3 says, which atom gives up its electrons most readily? So we're going to be looking at aluminum. Let's see. If you read them off to me, we've got Al. What's the next one? Boron.
Iron. It's they're all in the same.
Yeah.
Okay. So we're looking at those 4 all in column 3A. Okay, so we're comparing a pure column or row, which means our periodic trends are easier. Right? If we had something where we're comparing across diagonally, it's a little bit more subjective, but okay, they're all in a row here. It says, which one of those gives up its electrons the most readily? Right, IN. We're looking at ionization energy, or ionization potential there. So, which one holds on to its electrons the strongest? And the trend is, the higher, the stronger the hold. And you can remember that also by thinking, hey, think of these as planets, though we know it's not perfect like planets, right? It's not like circular orbits where we got different shapes going on, but if we tend to think of it like distance from the nucleus, we could say pretty confidently that the elements, the farther down you go, are farther away from the nucleus. And the farther they are away from the nucleus, the easier they are to steal. Because the closer they get to the nucleus, the closer they are to the positive charges, the closer the greater the bond between that negative electron and the positive nucleus, so the protons. So it's harder to steal them when they're tighter. They're easier to steal when they're farther away. Right, so that's why the ionization energy increases as we go up. So it would be hardest to snatch from boron, but it would be easiest to snatch from ion. Number 4, order the following atoms in terms of increasing ionization energy. SR, SB, column? Okay, SR.
They're all in the same column.
Well, just going back to make sure I get the right ones. SR, SB, and I.
It's got listed.
Okay, so now rather than looking at a column, we're looking across in a row. It says, which of those 3, or put them in order in terms of increasing ionization energy. So ionization energy increases if we wrote the diagonal, which is, we can say it increases in this way, it also increases in this way, and that's why I represent it on the table as increasing in that direction. We do the vector math and say increases up, it increases to the right. I can show that by using it increases on that upper diagonal. So in increasing order, they would go which way? SR, SBI, good. Straight across. So they are written from left to right in increasing ionization energy order. Yes, sir.
You wanted me to tell you when it was time.
Okay. We've had too much fun early. Let's keep cruising. Number 5 is the next one that you asked for. Which atom has the greatest desire to attract electrons? You've got nitrogen, NSBAS. What do we call the desire to attract electrons? Electronegativity. The trend on electronegativity is the same as the trend on ionization energy, right? They both increase in this up and increase right. So which one has the greatest desire? Nitrogen does. So nitrogen has the greatest desire for the additional electrons. Okay, number 6, these are quick. Order the following in terms of increasing atomic radius. Well, I know AS is one of them, right? What are the KBR? So we got K. What's another one? Like that? That one's over here. Okay, in terms of increasing radius. And what is the trend in increasing radius? So, in this direction. So, as we look at increasing radius, how do they go in these 4? How are they placed in order? Right, they go from right to left in increasing radius. So potassium, the 4s1 molecule actually has a greater radius than over here at the 4s2, 4p6. More electrons, but they're pulled in tighter to the nucleus because for every electron you also gain a proton. Draw the structure for CH4. Did anybody have difficulty for 6 or number 7? No. No? Pretty straightforward? Okay, so you had a carbon with 4 nodes. And each one of those nodes had a hydrogen attached to it. So C, it's a metal and non-metal, and it looks like that. It's a tetrahedron. CH4. The Lewis structure for PCl3. I'm going to go ahead here and just assume that I'm going to need, I'll set it up like this, right? Start to see the symmetry that takes place of PCl3. Yes, ma'am?
Please see Aaron Rice when class is over.
Yes, ma'am?
Okay.
So PCl3P, phosphorus over here. What's this Lewis look like?
5.
It's 5, okay. Again, I get a little inside information on this, but I know that since I'm going to go ahead and depict it like that. You see the 5 around? Chlorines have 7. I'm going to orient my opening towards the center. I'm going to put the remainder. Okay. This is a 2 nonmetals, so it's a covalent bond. So they don't give up any, they share, and they share like that. Potassium chloride. What is the Lewis structure for FNO? Does anybody else need this, or you got it? FNO. FNO. These are all needy nonmetals, right? Covalent bonds. N, F, and O. N is a 5. O is a 6. S is 7. And 7, okay, so we have here. I didn't know what the chatter was about, so. This will actually cover what we were going to address with the other question. I think we're going to see this here. In order to complete my fluorine, how many electrons do I need? 1. I'm going to share my 1. Now see, nitrogen has the most number of open slots. You see that? There's 3 open slots. There's 2 here and only 1 here, so I put it in the middle. When I share 1 across, now this guy's all done. He's got what he needs to have 8. 1, 2, 3, 4, 5, 6, and a shared 2 makes 8. 1, 2, 3, 4, 5, 6. How many more do we need here? We need 2. Okay? So I'm going to share these. That's my 1 share. And I'm going to bring up and share 2. So F and O. A single bonded and a double bonded. It didn't do what I thought it was going to do. Based on number 10, just looking at your book, based on the Lewis structures, which is the easiest to break between those 3?
H2.
H2 would be the easiest. Then would be C2H4 and then PN. Why would PN be the hardest? Triple bond. Yeah, it has a triple bond. So it's a triple bond, a double bond, and single bonds. The hardest one to break. Now, you would technically be breaking up the C2H4 because it has single bonds in there too. So the single bonded H to H and the single bonds between the carbons and the hydrogens on those 2 molecules work out to be comparable. So the PN with the triple bond, that's the one that is the hardest to break. The question that I wanted to cover real quickly before you go is on your homework for tomorrow. And you have the formula we're trying to solve in front of you?
What is the Lewis structure for CS?
CS. If you haven't seen one like this, I want you to know that this is a possibility. For carbon, how many?
4.
4. Sulfur? 6. Watch what we do. Carbon has 4, sulfur has 6. Carbon wants to have 8. Let's start sharing. 6. How many is over here? 1, 2, 3, 4, 5, 6, 7. Okay. Another double bond. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Sulfur is satisfied with 8. Carbon only has 6. It needs 2 more.
I don't get that.
All you're doing is carbon still needs to have more electrons in it. It doesn't have them. Sulfur doesn't lose any by sharing 2. See? We got to this place here. This is the part that makes sense to most people. You got the 2 carbon electrons sharing with sulfur, sulfur sharing 2 electrons back. People are fine with that. But if you look at carbon, how many valence electrons does carbon have now? 1, 2, 3, 4, 5, 6. How many does it need to have? 8. How many does sulfur have? 1, 2, 3, 4, 5, 6, 7, 8. If I take a pair and share them, now how many does carbon have? 1, 2, 3, 4, 5, 6, 7, 8. How many does sulfur have? 1, 2, 3, 4, 5, 6, 7, 8. We get both electrons from the sulfur atom.